Okay, I'm sharing my screen. Okay, yeah. Okay. See here, today we'll start the behavioral modeling in the Verilog. Okay, so basically behavioral modeling and data flow modeling we call as RTL code. Okay, what is this behavioral modeling is there? So behavioral modeling is nothing but I told you in the starting class. That means we know the behavior of the circuit, so no need to worry about internal circuitry. Okay, suppose if you consider the half adder, I know the behavior of the half adder, but I don't bother about the internal logic or internal circuit of the internal circuit. So that is nothing but behavioral modeling. Okay, so what is this behavioral modeling? We'll see today. Okay, so behavioral modeling. 1 second. Okay, yes. My screen is visible now. Just to give response so that I will move forward. My screen is visible now. Yes or no? Yes, give response. Shall I move forward? Behavioral modeling. Okay. Okay. So I hope my screen is visible. Okay. So behavioral modeling. Okay. Behavioral modeling. So what is this behavioral modeling? So in the behavioral modeling, you have this is a structural procedures are there. Structural procedures. Okay, what are the structural procedures? Those are we have initial block. Okay, we have initial block and initial block. Okay, and always block. Okay, initial block and always block. Okay, so what is this initial block? So what is this initial block? Initial block is nothing but it execute only once. Okay, it will execute only once. Okay, only once. Okay, and so when it reaches end of the block, end of the block, it will execute only once. Okay, reaches end of the block. Okay, and this is non-synthesizable. What is non-synthesizable? I told you synthesis, no? So this is non-synthesizable. So non-synthesizable means we by using initial block we can't convert this one into hardware. Okay, so this is non-synthesizable. We can't convert this one into hardware. Okay, 1 second. This is initial block. Okay, initial block is what non-synthesizable. Okay, so initial block is non-synthesizable. So we cannot convert into hardware. Okay, so we can't convert into hardware. That is nothing but non-synthesizable. Okay, and always block. So what is always block? So the name itself it is this always. That means always means what we can say that forever. Okay, so this will be repeat continuously. This will repeat continuously. Okay, continuously. Okay, and during the simulation time. Okay, it will repeat continuously during the simulation time. Always, that means we will write like always at the rate suppose if it is like full adder circuits is there, so that means if we can write half adder is there means a comma b. Okay, this is nothing but we call as sensitivity list. If there any change in this input, so there is a change in the output. Okay, so that means you have some 100 in outputs are there, so we can use always block, always at the rate star. This is nothing but implication operator, so we will discuss this. So always block is essential element of RTL behavior. Okay, so this always block is this is the essential element. Okay, so this is the essential element for RTL and behavioral modeling. Okay, RTL and behavioral modeling. Okay, behavioral modeling. Okay, RTL, register transfer level, I told you, no? Okay, and suppose if you are writing block of statements. Okay, if you are writing some block of statement, multiple statements, you need to write within the initial and begin. Okay, you need to write between the initial. Okay, so initial, some statements are there, some block of statement, and you need to write so initial so not initial, you need to write within the begin and end. Okay, you need to write within the begin and end. Okay, begin, and it will be end with the end. Okay, this is the keyword. Okay, it should, so group of statements within the keyword we need to write between the begin and end. Okay, so how the order of execution? The order of execution is from top to bottom. Order of execution is from top to bottom. Okay, so if you see the initial block, okay, if you see the initial block, how it will look like means, see here. So initial block, so So initial block. So if you see the initial block, so basically initial we are using in the test bench, and sometimes we can use in the design also. Okay, if you see, one second. Okay, so what is this initial block? The block of code start with a keyword what? Initial. So that the block of code, it will start with initial. Okay, initial, and when it will start at 0 simulation time. It will start at 0 simulation time. Okay, 0 simulation time. And suppose like if you take the one example, initial begin, reset equal to 1 tick binary 1, reset equal to 1 tick binary 1, and this is #10, and reset equal to 1 tick binary 0. Okay, and in equal to 2, and #10. Okay, #10, and next in equal to 3, and end. Okay, like this. Okay, so this is so execution stops when last statement is executed. Okay, when last end statement is executed, that execution will stop. Okay, so this is the initial block. Okay, and so initial block will be executed only one time. Okay, so the initial block will be executed only one time. So this is about the initial block. And next is always block. Okay, so in the always block, so this always block, this loop is controlled by, so loop controlled by events. Okay, loop controlled by events. Okay, loop controlled by the events. Okay, so this always block, the code will start with a keyword. What is the keyword you are using? Always. Okay, you are using a keyword called always. Okay, so event there is any change in the on the register or net, then there is a event. Okay, what is a event? Event is nothing but there is any change in on register or net, then event occurs. Okay, there is like I told sensitivity list. Okay, so sensitivity list means, so that means you need to write the sensitivity list. Suppose if it is a full adder, always at the rate, what are the inputs? A, B and C in. So that means this is a combinational circuit. If there any change in these inputs, there is a change in the output. These are nothing but sensitivity list. We can call this as a sensitivity list. Okay, sensitivity list. Okay, so suppose like you have a design, you have some design, 100 inputs are there. 100 inputs you can't define in the sensitivity list, no? So in that I can use the like always at the rate star. Star is nothing but what? Implication operator. This is nothing but what? Implication operator. So if you are performing this star, so this star is allocated for all the inputs. If there any change in that 100 inputs, then there is a change in the 100 outputs. So in order to indicate all the 100 inputs, I can use this implication operator, that is star. Okay, so I can use star also. Okay, so like this. Okay, and so suppose we can use like this also, always at the rate passage of clock. Okay, in the sequential circuit, always at the rate passage of clock, and we can use always at the rate neck edge of clock. Okay, so that means output will change during the passage of clock. So that output for the flip flops, if you positive edge trigger flip flop means the output will change, the output will be trigger only during the passage of clock. This is the passage of clock. Always at the rate negate of clock means what? The output will change during the negate of clock. Okay, during this negate of clock only the output will change. Okay, so that means from here what I can say, what is passage? So the passage is detected. Okay, so when it will be detected, so it will be detected when transition happens from 0 to either x, z or 1. Okay, or transition happens from x, z to 1. Okay, xz to 1. Okay, xz to 1. Okay, transition happens. This is nothing but passage of clock. Okay, and what is this negate of clock? So 1 second, somebody is there in queue. Okay, okay, what happens? Any doubt? Queue response? Okay, yeah. Okay, my screen is visible now. Yeah, anyone? Okay, okay. So this is nothing but passage of clock. Okay, and so any doubt or any query you can ask me. Okay, next negate. So what is negate? Is when it is will be detected. Negate is detected when it is changing from where to where, 1 to x, z or 0, or it is changing from x, z to 0. Okay, this you need to remember. Okay, so suppose if you want to write execution of trigger in a positive edge of clock. Okay, how to write the program? Suppose I am writing the execution of triggering during the positive edge of clock. Okay, positive. Okay, positive edge of clock. When you are writing positive edge of clock, 1 second. 1 second. Positive edge of clock. So you are executing the triggering on the positive edge of clock. Okay, positive edge of clock. Positive edge of clock. So if you see, so always at the rate passage of clock. Okay, passage of clock, and begin. Okay, if reset, that means what? If reset equal to 1, so you are making what? Q is initialized to what? You need to use non-blocking operator for the sequential circuit. You need to use 1 tick binary 0. Okay, else Q is related to D. Okay, this is the basic we can write D flip flop. Okay, this is nothing but we are writing for the D flip flop. That is positive edge triggering positive edge of clock. Okay, the output will change during positive edge of clock, and active high reset. Okay, this is a basic simple program. Okay, so how it will look like? So that means here it will be like the how the program will be there in the behavioral modeling means always at the rate triggering of pulse. Okay, triggering of signal, either it is positive trigger signal. Okay, always at the rate trigger signal begin, and you have procedural statement. Okay, and some more procedural assignments are there. Okay, procedural assignments. Okay, end like this. Okay, so you can write like this also. So always I told you, no, I can use this implication operator, that is always at the rate star. Begin. Out equal to what? So if you are using combinational circuit, you need to use blocking operator, and if you are using sequential circuit, you need to use non-blocking operator. Okay, so ARB, okay, and C and C and XOR of D, XOR of D and end, like this you can do. Okay, this is always block. And next you have some procedural statements also there that we can use in the behavioral modeling. Okay, so what are these procedural statements, we'll see. Okay, so procedural statements, so procedural statements, if you see, so determines the flow of data and operations. Okay, determines the flow of data and operations. Suppose in the procedural statements you have conditional statements. What are the conditional statements? So conditional statements are like if else, and case. These are the conditional check. It will check for the condition. If condition is satisfying, then it will execute that operation. If condition is not satisfying, it will come out of that loop. Okay, and next you have loop statements. Okay, so what are these loop statements? Loop statements are while, for, repeat, and forever. These are some looping statement. Okay, so these are so that means which control the simulation and manipulate the variables of data. Okay, so so these are some. So basically these conditional statements and loop statements we are basically using in where C programming, no. So if you know, if you are comfort in C, so you can understand very well. This is same as whatever we are using in the C program. Okay, this is like a traditional programming language such as C only. So you are using in C only. In C also you are using if else, case, while, for, repeat, forever you are using. Okay, so we'll see some syntax of this. Okay, what is this if condition, if end. Okay, so if it is if condition, okay, begin, if condition begin, so it will execute. Okay, code. So whatever the code, so whatever the condition is true, this will code to execute whatever the condition will true. Condition is true. Okay, condition is true. Okay, else, end, else, code to execute. Okay, one second. Okay, so code to execute here, whatever the condition is false. Okay, whatever the condition. Okay, code to execute, if condition false. Okay, condition false. So that means if condition is true, so it will execute the true condition. Okay, if condition, else it will execute the false condition. Okay, and this is if statement. And case. So how the case will look like case, you need to use selector. And here you are using value 1, and code for value 1. Okay, you are using code for value 1, and value 2, next code for value 2, okay, and so on. For if statement, you need to have the default statement. Why? Because when you are writing the MUX code by using case statement, this case statement should have the default statement. Why? Because if without default statement, it will go into latch. Okay, it will inferred as latch. Okay, so that's why case statement should have the default statement. Okay, so this is code for default case that I will show you for the MUX. Okay, code for default case, and end case. Okay, so this is for what case. Okay, and next if you see the while. Okay, while statement, how it will look like. So while means so while condition begin. Okay, so code to repeat, repeat while condition is true. Till the while condition is true, this will execute this instructions. Okay, this will execute these instructions and end. Okay, so this is nothing but while loop. Okay, for loop, how for loop will look like? So that means for loop, I think you know the for loop. So it will be look like this. So for loop, for let us take I am using I equal to 0. This is nothing but initialization. I is less than 8 and I equal to I plus 1. Okay, so in Verilog, so in C you are using what for increment, it will be I plus plus, no, but in Verilog if you are giving I plus plus, it will not take, you will get the syntax error. Okay, but in system Verilog it will take. Okay, we can give I plus plus also, but in Verilog you need to give what I equal to I plus 1. You need to give I equal to what I plus 1 and next begin. Okay, so this code will be repeated how many times? So code repeats for how many times? 8 times. Code repeats for 8 times and end. Okay, so this is about code repeats for 8 times and end. Okay, so this is for loop and forever. Okay, forever. So forever, so forever means what? Whatever the statement is there, that statement will be statement to be repeat indefinitely. Forever, continuous, indefinitely means infinitely it will be repeated. Okay, and repeat also. So what is this repeat? So if you see the repeat will be like this. Repeat, here you give value. Okay, so the code will repeat how many times? Code to repeat, so code to repeat three times. Code to repeat 3 times. Okay, and end. Okay, so like this we can do this program. Okay, hope you understood the behavioral modeling. Okay, suppose for the MUX I will show you. Okay, behavioral modeling. 1 second. Okay, 1 second. Verilog programs, full adder using half adder, some I will tell you multiplexer design, no? So multiplexer design we'll see. Okay, so this is multiplexer design. Okay, so I am opening the Xilinx Vivado. Okay, this is what okay, yeah, I will tell you. 1 second. So here I wrote the multiplexer program. 1 second. RTL codes MUX multiplexer. Okay, so multiplexer RTL codes I wrote. So see here, so I wrote with different cases. What are these different cases? 1 second. So view large icons. Okay, so by using if statement. Okay, this is data flow modeling. Okay, data flow modeling, I think you know. So like so this is nothing but which MUX, so 4x1 MUX I wrote by using data flow modeling. Okay, so if you see the 4x1 MUX, so that means it will start with what? Module MUX 4x1 4x1 data flow modeling. So I am using what? Input wire 3:0. 3 is to 0 means how many inputs are there? 4 inputs are there, D0, D1, D2, D3. And how many selection lines? 2 selection lines are there, 1 is to 0. So 2 selection lines will be there, and output wire y, okay, and output, okay, assign y equal to what? Selection. So that means assign, I need to use the continuous assignment statement no, for data flow modeling. So assign y equal to, if selection line equal to what? 0 0 d, so D0 is connected, okay, or if selection line equal to 0 1, D1 is connected to the output, y equal to D1. If selection line equal to 2 tick binary 1 0, D2 will be connected. If selection line equal to 2 tick binary 1 1, so the D3 will be connected, or otherwise 1 tick binary X, okay. So this is basic data flow modeling, okay. So for the test bench also I wrote, okay, TB I wrote, okay, data flow modeling. This I will execute and I will show you, okay. So how I wrote the test bench? So here you see, so how I wrote the test bench, data flow modeling. See here, module TB MUX 2 cross 1, MUX, this is 4 cross 1, okay, this is 4 cross 1 data flow, okay, 4 cross 1 data flow, okay, I am using 4 cross 1 data flow. So reg, whatever the inputs are there, I need to initialize to reg data type, and whatever these outputs are there, I need to initialize to y data type, and I am instantiating, okay, I am instantiating this by connection by name, and outside the bracket are nothing but design signals, and inside the bracket are nothing but test bench signals, and I am initializing integer I, and initial begin I am using for loop. So that means I am using for 8 combinations, okay, selection line A and B, okay. I think this is 2 cross 1 MUX, 1 second, 2 cross 1 MUX, TB data flow 4 cross 1 MUX, I will tell you if statement, okay. Okay, so see here, that is data flow modeling. If statement you see, this is the if statement, okay. We are writing with behavioral modeling, okay. So if you see the behavioral modeling, see here, so module MUX 4 cross 1 MUX, same thing, initialization. So I am using the vectors, so 3 down to 0. So how many inputs? 4 inputs, D0 to D3, and selection lines 1 down to 0. How many selection lines? 2 selection lines. And if you are using behavioral modeling, the output should be reg data type, okay. This you need to remember, output should be what? Reg data type, okay. Always at the rate star begin, if selection equal to 2 tick binary 0 0, y equal to what? D of 0. Else if selection equal to 0 1, y equal to D of 1. Else if selection equal to 2 tick binary 1 0, y equal to D of 2. Else y equal to D of 3. So this is by using if else statement, okay. So this is by using if else statement, and I can write using case statement also, okay. So this is the MUX code by using case statement. You see this, so this one, 1 second, this one, so I am initializing the input way by using vectors to D0 to D3, and selection line 1 down to 0, output reg y, okay. I need to initialize always at the rate star. I told you, no, implication operator, I can use the inputs, okay. I can use here, how many inputs are there? So that means inputs are nothing but I can use the inputs D comma selection also I can use, or I can use what? Implication operator, that is star, okay. So that means that will be applicable for all the inputs, okay. Case select, so this is the value, 2 tick binary 0 0, y equal to D of 0, 2 tick binary 0 1, y equal to D of 1, 2 tick binary 1 0, y equal to D of 2, 2 tick binary 1 1, y equal to D of 3. And I told you, for case statement you need to have the default statement, okay. Why? Because if you are not having the default statement, it will infer as a latch. That means it will go to the previous state, okay. It will like infer as a latch, okay. That's why you have the default statement y equal to 1 tick binary x, and end case end module, okay. So this is nothing but case statement. So first I will execute the if else statement, okay. You can see the test bench also. See here, test bench by using if else statement, okay. So this is the test bench by using if else statement. See here, I wrote the test bench, okay. So module TB MUX 4:1 if else if, so whatever the inputs are there, that I am initializing with reg, okay. I am using a vector 3 down to 0, so like 4 inputs are there, and 2 selection lines 1 down to 0, wire y. So I need to instantiate the design, so I am using instantiation by name, okay. So MUX 4 cross 1 if UUT is nothing but instance name, that is unit under test dot d so dot d, this is whatever the signals outside the bracket or nothing but design design inputs and outputs, and whatever the signals inside the bracket are nothing but test bench inputs and outputs. Okay, so through the test bench you are giving the test cases through the design, and design will give the output to the test bench. Okay, so integer I, and initial begin dollar display. So I need to display this. Okay, selection D in Y in TCL console, and I'm using for loop for I equal to 0. So how many combinations? So like here 4 inputs are there and 2 selection lines are there. So I need to see for how many combinations. 4 plus 2, so 6. 2 power 6. 2 power 6 is 64 combinations I need to check. Okay, so I is less than 64. I equal to I plus 1. I am using concatenation operation. Select comma D. I equal that is equal to I, and for 10 time units I am displaying these values. And I want to finish the simulation. I am using $finish. Okay, test bench for if else also same, but in case also same, but what change you will get? Only in the instantiation you will get the change. Okay, so in the instantiation, just you need to instantiate case. Okay, remaining all are same only. Test bench both are same only. Okay, so like in the combinational you have like 4 methods are there. So like you have like you need to initialize the internal variables, and you need to instantiate, and you need to give the test cases. Okay, only three steps are there. Okay, so the like this I am giving the test cases by using for loop. I am giving the test cases. So this I want to load this. Okay, I want to create. Okay, so just in this only I am doing. Okay, in this MUX only I am doing. Okay, is it fine now? MUX program, any doubt or any doubt? Any doubt? Shall I move forward? Give response. Yes. Okay, so this one I am executing. So first copy this, add the design source. Okay, create the design source. So what is my design source? In this data flow modeling I am not doing. First I will do if else. Okay, so what is my design source? MUX 4x1 MUX if. Okay, so this is just to copy this and add the design in the Xilinx Vivado finish. Okay, so module name is also same. Yes. Okay, module name is also same. Okay, so this one I am copying this file. Oh, which one? If. Okay, MUX using if. Okay, MUX using if. Copy this, just paste in this. Okay, save this. Okay, save this. Okay, so this design is created. So I want to see this design. So right click and set as top. Right click, set as top. Okay, I can make this a set as top. And simulation. So go to simulation, add the simulation. So add the test bench. Okay, what is the file I need to add? Test bench file with related to this one. Okay, so this file I need to add. Okay, so this file and that file should be same. Okay, so copy this and add this is my simulation file, tb mux 4x1 if finish. Module name also I want same only. Okay, so I am adding that file. Okay, so what is that? This file I added. Okay, which one? This one. Okay, this one. And what is that? If else statement, no? So test bench I am adding. Okay, test bench I am adding. Copy this. Okay, and just paste this and save this. Okay, I got end module. End module. Okay, end module, save this. Okay, it will be added. Okay, after that I want to design. So I want to see the elaborated design. See here, by using if else statement how we are getting, we'll see. Okay, by using if else statement how we are getting the elaborated design, we'll see. You are getting like a what priority MUX. Okay, like priority MUX you will get. Okay, we'll see the elaborated design. Okay, priority MUX you will get. 1 second. Yes. Okay, yeah, I'm loading my design. See here. So like 2x1 MUX connected, like priority level you are getting the elaborated design. Okay, priority level you are getting this elaborated. If you elaborate this there, you're getting like a priority mux. Okay, it's like a priority mux. Okay, I'll show you in the case also. And if you run the simulation, so what you are getting, we'll see. So if you see, if you elaborate this fit to page, okay, I will get what different combinations. Okay, when S1 S0 or 00 for different combinations, A and B. Okay, A and B I will get. Okay, so that means Y output I will get. Here you see, depending on the selection line. Okay, selection line S0 and S1. So these are connected to the output. Okay, so like this I will get the 64 combinations. For 64 combinations I will get this output. Okay, like this. Okay, this is the simulation part. Okay, I am closing this simulation. I am closing this elaborated design. So by using case statement we'll see. So by using case statement, so where is my case statement? If statement is completed, no, I am closing this. This is case statement. Okay, so this design I'm copying. Just copy this. Okay, and in Xilinx Vivado, design source, add this source, add the design source. Next, create the design. This design. Okay, 4x1 mux. Finish. 4x1 mux. Okay, yes. Design source is created. Okay, so this is case statement. This is case statement, and this program I am copying. So copy this. Okay, and paste in this. Okay, always at the red star. Syntax error. Always at the red star begin. Okay. Okay, here syntax error is there. Okay, semicolon is missing. Okay, that's why. Okay, always at the red star. Here semicolon is missing. Okay, yeah. So yeah, so output reg y. So save this file. 1 second. Case select. Okay, here close the bracket. No, I need to close the bracket. 1 second. So I need to close the bracket and semicolon. Now it will go. Okay, so I'm okay. Select comma output. Always at the red star begin. Okay, always at the red star begin. Okay, always at the red star begin. Okay, and next tb. So this tb file. Okay, tb file. So copy this, and in the simulation sources, add this source. Next, create. Okay, finish, and I am using this mux. Simulation source is created. Okay, so tb 4x1 mux. Okay, just copy this testbench file. So copy this and paste in this. Okay, paste in this and save this. Somewhere syntax error. End module is missing. Okay, end module. Okay, save this. It is added. Okay, after that, so whatever I want to simulate, that you need to make as top module. Set as top. Okay, and next I want to elaborate the design. Okay, if I want to elaborate the design, right click, set as top. Elaborate the design, set as top. Okay, elaborate the design. Okay, I'll see the difference when you are writing the program by using if else statement. You got the netlist, or you got the circuit in terms of what, in terms of priority mux. No, so here by using case statement, if you observe, you are getting same as 4 cross 1 mux. I think have you seen the difference? Okay, so by using this by using if else statement, you are getting what if else statement, you are getting what schematic, we already seen the schematic, no, last schematic, if else yeah, you got the schematic, so there you got what you got with 2 cross 1 muxes, 3 2 cross 1 muxes are you are getting in terms of priority level. Okay, in terms of priority mux you got by using if else statement, but by using case statement you are getting as it is, the mux as it is you are getting. Okay, so 2 selection lines, 4 inputs and 1 output. Okay, so like this you can see the elaborate design. And so run the behavioral modeling, run the behavioral modeling, and depending on the selection line, the output is connected to the input. Okay, you will get the waveform. Okay, so this waveform you will get, so fit to page. Okay, so depending on this selection line only, the output will be connected to the input. Okay, if it is 1 1 which is connected, so 3 inputs are there, no, so 3 inputs are there, so 1 1 1 1 you are giving different possible combinations. Okay, you can see here also. Okay, here also, so depending on the selection line. Okay, so if selection line equal to what, selection line equal to 0 0, which one is connected, I0 is connected to the output. Okay, I0 is connected to the output. In selection line is 1 0, I1 is connected, like this. Okay, depending on the selection line, you are getting whatever the output of this I1 is there. So here you see, so selection line is 0, you are whatever the output input of I0 you are getting at the output. If selection line equal to 1, okay, whatever the input, whatever the inputs of this I2, okay, I2, so I1, these I1 you are getting at the output. Okay, you are getting at the output. Okay, like this you can see the see here, whatever the I1 output is there, you are getting at the output Y. Okay, at a time any one of the input is connected to the output, no, depending on the selection line. So like this you can see the, so if it is 1 0, if it is 1 0, selection line is 1 0, so which is connected to the output, this D2 will be connected to the output. Okay, the D2 signal, whatever the D2 signal is there, that you are getting at the output. Okay, and if selection line is 1 1, you are getting the signal of D3. Okay, you are getting the signal of what, D3 you are getting. Okay, so what is D3? D3 is what here, this signal, this D3 signal you are getting at the output. See here, so how the D3 signal is there, same like that you are getting at the output. Okay, so like this we can analyze the simulation for the 4 cross 1 mux by using case statement, and also we can analyze the schematic. Okay, how the schematic will be there, it's like a same 4 cross 1 mux only. Okay, this is about today's session.